You can all come forward. It'll be easier. Okay, so what we will do in the second lecture is to talk about one of the most interesting and enigmatic objects that can be detected with radio astronomy, and it's primarily via radio astronomy, called pulsars. Okay, and like I was saying earlier in the introductory lecture, radio astronomy allows you to detect different objects. And as we said, some objects you can see in optical also, and the radio gives you a complementary view, just like we were discussing about the X-ray and the ultrasound giving you a complementary view of what's happening in your body. But there are some objects which can be seen primarily only in radio. So it's just like saying that the X-ray, if you want to see the bones in the body, primarily X-rays only. Other mechanisms will not show you the bones of the body. Okay, so these neutron stars or pulsars happen to be one of those objects which are primarily seen only by radio waves. In fact, if radio astronomy had not been there, maybe we wouldn't have detected them even till today. Okay, and there are similar objects in astrophysics which have this property that only certain kinds of radiation or signal they give out, and you can therefore see them only with those kind of detectors and in that branch of astronomy. Okay, now let's start about this, and what we'll do is introduction to pulsars, a little bit about how a radio telescope observes pulsars, and then some interesting aspects about neutron stars. Okay, and we'll see when we run out of time we will stop. Okay, so and as I was doing in the earlier lecture also, this is not just me talking. You all are welcome to participate, and as he was saying, can I ask questions? Feel free to ask questions in between, and in fact I'll ask you some questions if you don't ask me questions. Okay, all right, so who will tell me what they understand, what is a neutron star? There you go. Yeah, go ahead.
A neutron star is when sometimes there are two things a star can turn into once the supernova has happened. It's a neutron star or a black hole. One main difference is that the neutron star gravity is not that strong, so it can allow light to escape. So if you can see something that, then you can understand, if you want to check these two things, that it's a neutron star. But there are other things a neutron star has. For example, it is mainly composed of degenerate neutron matter, and it is not that large as most stars. It gets very small because of the density.
Yes, I think you can come here and give the talk with me. Very nice, good. So that's very good. So the two important things there are that these are very dense and very compact small objects, which are one of the end stages of evolution of a star, right? And you said many of the things there, including supernova and all that. So that's where we will start with, that how a neutron star is born. Okay, and then we'll go on to see. So how a star evolves and where it ends up depends on what the initial mass of the star is, and this is something very interesting. So we all know that our sun is a average size star as far as size and weight is concerned. Okay, it's not a very small star, nor is it a very light star. It's a sort of a medium range star, and a star like the sun, and again some of this you will know that it has lived for a few billion years, and it will live for another few billion years. And you can ask, what does live mean? When is it living and when is it not living? Is that from the time it formed from a large ball of hydrogen gas. Okay, that is what we all understand, that when the cloud of hydrogen gas starts to contract and collapse because of gravitational force of attraction between the molecules in the gas, the atoms and molecules in the gas, then it starts becoming smaller and smaller and denser. And if you can't stop that, then the gravitational force will keep pulling it closer and closer and nearer and smaller and smaller. Okay, so in any star, what happens is that some force or some action happens which balances the pull of gravity. Otherwise, matter will keep falling in as long as there is gravitational attraction. Okay, and in a normal star, this happens the moment the density of this collapsing cloud of hydrogen reaches at the center enough density to start thermonuclear fusion. Okay, so that reaction, which is a nuclear reaction, which is, if you go to the main pavilion, there is this project called ITER, right? The ITER is the aim to build a nuclear fusion reactor in the lab on the earth, so that you can generate energy. So that is what this reaction does at the core of the sun. It generates energy and heat, and that thermal energy then is like a pressure. It balances the force of gravity trying to contract, and so then you get an equilibrium state. Okay, so what it means is, as long as you can produce this heat and energy from the center of the sun and produce enough pressure so that it balances the force of gravity trying to contract, the star will remain in balance, in equilibrium. Okay, and so you say, okay, how long can this happen? Well, as long as this reaction can keep going. Okay, and this reaction requires fuel, in the sense that hydrogen is being combined in an atomic reaction to produce something heavier, that is helium. In the process, a certain amount of energy is being released. That energy produces the thermal pressure, which balances the force of gravity. So obviously you will say, well, when all the hydrogen finishes in the core of the star, then there is no more hydrogen left to burn, and then it will have no more fuel and no more reaction, and then again, therefore no heat and no energy, and then the force of gravity will again take over. So in a star that does happen, but then the star starts burning the helium. So there is another nuclear reaction where helium can combine when the pressure becomes sufficient into heavier element, again releasing energy. Okay, so you go to carbon, you go to nitrogen, oxygen, so on, and you go to the point where iron is formed. Okay, now when you try to combine iron nuclei into a heavier element, that reaction is no longer exothermic, it does not release energy. So all these other reactions are such that at the cost of a little bit of the loss in the mass, energy is being released, and that is keeping the balance. So when that happens, the star has no more fuel in the center to keep this balance, and at that point the gravity causes the star to collapse. Okay, now what happens then depends on how much matter there was in the star. Okay, so the stars which are very heavy, much larger than the sun, they have much bigger cores and a lot more hydrogen, but they also burn this at a much faster rate. Okay, so they will go through this different cycle where hydrogen fuses to helium, helium fuses to carbon, and so on, and at the end they reach this stage where this central thing, there is no longer, it has now formed iron, and it cannot do anything beyond that to produce an exothermic reaction which can produce energy. So at that point, there is so much material still around in this huge star that was the original parent object, that there is a sudden collapse because of the force of gravity. Okay, and there is a implosion of the core. So there's actually, so this is a complicated reaction that happens, that the force of gravity causes the star to collapse, and then there is an explosion that happens in the center, and the whole star blows up. Okay, that is what is called a supernova. Okay, and that is a very bright event which when it goes off, it produces so much light and energy from, it's like a firecracker going off, like, okay, you can think of it like that. Yes?
Why does the rate of burning of that fuel is higher in bigger stars?
Because simply, you know, the volume is more, and it is having to support a much larger mass against gravity. So it has to then burn more fuel in order to.
More fuel is available, hence burning more.
And also, if you don't burn that much, there is a huge amount of mass waiting to collapse. So the force of gravity is higher. So it has to generate more energy.
So they die out faster?
They die out faster. So you know, it is they evolve much faster than the normal. So our sun is doing this. So for last few billion years, it has been burning hydrogen, and it has enough hydrogen that it will do it for another 4 or 5 billion years. Okay. After that, our sun will run out of hydrogen. It may go into the next cycle. Okay, but there is not enough mass in the sun to go into this supernova state. It will end up in what is called a white dwarf star. Okay, and that evolution is slightly different than this. So what the star ends up in, a lot of that is decided by what its original mass was, because that dictates what happens, and then that sequence just runs a certain course. You cannot sort of change that, because you know it has that much material, and certain amount of reaction and certain things will happen. So you're right that these heavy stars, they evolve much faster, and they therefore reach this end stage where there is now no more of the enough fuel left for continuing this reaction. And in their cases, there is this catastrophic event that happens. In the case of the sun, you will not get such a catastrophic event. The white dwarf stage is like the embers of a fire, which is just a ember kind of thing is left, and you ask why isn't it collapsing, what is holding it against gravity? And there is something called electron degeneracy pressure, which happens when you reach that density, and a white dwarf will remain stable for many billions of years. Okay, here what happens is the outer the star explodes, only the core of the star collapses, and there that force of gravity brings it to the point where something very interesting happens, which I'll come to in a moment. But the outer parts just blow out, and this is a supernova explosion, and you get a remnant where this material is there, it's glowing for some time, and slowly it will fade away into the surrounding medium, what is called the interstellar medium in the galaxy. And you can see these objects as very bright nebulae in the sky. So some of the nebulae that you see are actually supernovae that have happened.
Why does outer part blow out when gravity wins?
Yeah. So actually, what happens is that phenomena that happens, it actually causes an explosion, a rebound. Okay. So the gravity is still winning over here. In the core, there is still a collapse going on. And I'll come to that what happens there. But so that physics is a bit complicated, that there is this both a collapse and a rebound, and the outer parts just get blown off, okay, in that explosion. The inner part, gravity is still pulling it down into a very compact object at the center.
Didn't rebound end with the fuel formation?
More fuel being formed. Yes, actually that's an interesting question. It does happen, but the way it happens is like this. So if you can imagine the cloud, the star formed from a cloud. In the cloud, there were certain regions where density became large, and therefore the star formed. There's still lots of gas in that cloud around that region where the star formed. And especially these big stars, which go through the life cycle very quickly, before that gas is dispersed, it goes to this explosion state. And that rebound, what it does is that it sends a pressure wave into this surrounding medium. It compresses that. It can compress it to the point where a new star can form. Okay, so it's slightly different from maybe what you had in mind, but it does do that. That rebounding material, it actually puts pressure in the surrounding tenuous gas which was there in the parent cloud, and there are parts of that cloud which can get compressed to enough density that a new star can start forming there. So it will trigger a new star forming from the death throes of the bigger and older star. So that is like a cycle that happens. Now you can ask, where does the cycle end? It depends on how big that original parent cloud was. Many times parent cloud will form many stars inside it, in spots where the density became high enough, and other regions which were less dense, in the second cycle they will start forming stars till the cloud finally runs out of enough hydrogen gas. Then you ask, where is other hydrogen gas in the galaxy? So that's a different story, but at the localized level that kind of thing does happen. Okay, so this remnant can be seen, and the important question that we are trying to ask is what happens at the center or at the core. Okay, so the core of the star actually is under the force of gravity, it collapses to a super dense star made up primarily of neutrons. Now, I'll come to a little bit of the details of that. It may be too technical, but one of the interesting things is that this theory of how a star will evolve given its original composition and mass was actually worked out by many people. And our Chandrasekhar was one of the scientists who did a lot of the work. And all these people, many of them predicted that, look, if you have a star of this kind of reaction will happen, this will happen in the core, and some compact object like neutron star should be formed. Okay. Now you say, well, you have a theory, how do I know such things happen? Okay, and there is no direct way of verifying. But at some point, people actually detected these objects, and that's where the story becomes interesting, when they got detected as pulsars, and I'll come to how that happened in a minute. So, okay, so the the collapsing part, so here what happens is, so this is what I was telling you earlier. I should have put this up front, that this is how the star lives in equilibrium between gravity and radiation pressure. And here you can see the various layers, where helium and then carbon, oxygen, silicon, the different layers at which the fuel is being burnt. And obviously the densest and the hottest regions are at the central core of the star. And then when iron forms at the core, so at that point the star looks a bit like an onion with different peels or layers, each containing rich and different species of the things which it has fused during the course of the reaction. Okay, and so now what happens when gravity tries to compress that remaining core which has iron nuclei? That an atom has a center which is which has protons and neutrons, okay, and then a large electron cloud, okay, and this is something that you will all have studied, that a bulk of the volume of an atom is filled by the electron cloud, and just a small part of the volume of the atom is the nucleus. But a large amount of the mass is in that nucleus, and a very small amount of the mass is in the electron cloud, right? So now, if you can imagine the situation where as somebody is trying to press and compress this, you would think that these electrons would get pushed and towards the nucleus of the atom because of the pressure, and somebody trying to just crush it. And that is sort of what happens. The electrons combine with protons to give neutrons, and then you get basically a sea of neutrons, okay, and there something called neutron degeneracy pressure comes in, okay, and this now goes into the details of atomic physics as to like electron degeneracy pressure. There is something called neutron degeneracy pressure, which means that when you have neutrons, you can't have them now too close to each other. If you try to put them closer than a certain this thing, there will be a certain pressure that will develop. Okay, now so this is now the pressure which can support the force of gravity. Okay, so in any such situation in a white dwarf, again it is electron degeneracy pressure which generates pressure which supports the star in equilibrium. In the normal star, it is the thermonuclear reaction which is generating energy and pressure which supports the star against the collapse of gravity. So in a neutron star, but in order for that to happen, as you can imagine, you have to take the electrons, the whole electron cloud literally has to be compressed into the nucleus. So when you do this, the two nuclei will come very close to each other. So and finally it will become just a sea of neutrons close packed with each other at the density of the nuclear matter. So in an atom, the density is the highest in the nucleus, and it is very, very high, okay, compared to the mean density of the atom, because rest of the atom is empty space with the electrons going around. So if you can get matter into that kind of situation, then you will have matter A with very high density consisting primarily of neutrons, and this force between neutrons creating the pressure which further stops gravity from getting the neutrons to come closer and collapse. Okay, and that's what he was saying, that if you go back and ask if the core of the star was even bigger, which would happen if the original star was even more massive, then even this pressure is not enough to support the tremendous force of gravity of a very large core of neutrons, and then that star will collapse further and it will become a black hole. Okay, which we won't go into today's lecture because that spans. Okay, but he has a question. Yes.
Sir, there's a big bounce theory, right? It says that. So according to what we know, according to what I know, it will say that means it will take infinite pressure to support the balance of the gravity, because there's infinite mass in the universe, right?
No,
So in the Big Bang theory it says that after that will again go into another universe.
Yeah.
But it has infinite gravity, so how can any amount of pressure balance it out? So how can it run into another universe?
Okay, let's do the following. Let's keep theories of different universe out of the current discussion. What we'll do is let's first talk about neutron stars and pulsars. After the lecture is over, we can talk separately about all these other things. There are many theories and models people have about what the universe looks like, how it may evolve, what may happen, and all that. But let's keep that for a separate discussion after the lecture. Okay, fine. So we'll keep this lecture because this topic is so interesting that once you go into black holes, then you will never come back to neutron stars and pulsars. Okay, so we'll keep this one confined to neutron stars and pulsars, but I'll try and answer things about black holes and rebounding universe or whatever else separately later on. Okay, fine. Anybody else? Yeah.
So you were saying in the earlier slides that a white dwarf and a neutron star both resemble a core of a remnant core of a star. So what makes them different to be classified as both?
Yeah. So it is again back to that same thing. In a white dwarf, there is not enough material so when it reaches a carbon core, there is a large number of free electrons that are produced. Electron degeneracy pressure is sufficient to support the remaining mass of the star. If the star was even heavier, then that is not sufficient. It will want to collapse further. At that point, then you get into this business of the iron core and the collapse to the nuclear density. Okay, and there is a different pressure force, the neutron degeneracy pressure, which is then sufficient to hold this in balance. But if it is even a heavier star to start with, even that is not sufficient,
so you find a black hole.
Then it collapses to a black hole.
So you can find individual atoms if you can find it in a white dwarf, which you can't find in a neutron star.
Yes and no, in the sense that whatever, I mean, as you saw, even when you reach a neutron star, the original parent star will still have this onion structure. Okay, it will have that, but most of that will get blown away in the explosion. What the core that will remain is just the iron core, and the collapse will go on from there. Okay, so even though the original star would have all of these, which is what the white dwarf would also have, much of these would actually get disrupted during the explosion. But the white dwarf does not go through an explosion of that kind when it forms.
It just blows it off.
The white dwarf evolution is different. Such a dramatic explosion as a supernova does not happen in that case.
So at such an extremely high temperature, there will be no atoms. I mean, ionization will be there, right? So and means it will be plasma.
It is a plasma, yes.
And in the case of plasma, we get some confinement of charges. So probability of falling of those electrons into the nucleus and getting converted into neutron is still high?
Yes, because in spite of the temperature, there is a very, very strong force of gravity. So, plasma is fine, but if you have very strong gravity, then, you can get to the situation where this kind of, phenomena occurs. Okay. So where the electron pressure is not enough, core starts to collapse as a supernova. Okay, so this is the situation where the forces are in addition to just the thermal forces due to the high temperature.
But sir, in the case of plasma, there is like area in which one type of ion get accumulated, or it is just a mixture of electron.
In this case, it would be a mixture of the different constituents that are there.
Confinement doesn't hold over.
It doesn't, not in the conventional way that you understand plasma confinement, because these things are generated differently and they are in a different environment in terms of both temperature, pressure and the force of gravity. Okay, so anyway, what we're trying to do is, delve into very complicated physics that happens in a very simple description or explanation, but just to understand that the phenomena is such that you get a core of what is predominantly neutrons, where the force between neutrons balances the force of gravity and keeps that object in equilibrium. Okay, and this basically requires the original star to have a certain amount of mass, which is like of the order of 8 to 10 times the sun's mass. So a star which is at least 8 to 10 times heavier than what the sun is. If it is much more heavier, then it will become like a black hole, as we were talking. Okay, now what happens is, in that process, that core of a star gets compressed to a size which is of the order of 10 to 20 kilometers. Okay, but the amount of matter in that core is still as much as about the total mass of the sun. Okay, which is many thousands of times more than the mass of the earth, for example. Okay, and you can ask, how can that be? How can that much material be packed into 10 or 20 kilometers? And that is because all of that is just nuclear density material. You have just removed all the empty space that the atoms were occupying, and therefore occupying so much of volume. Therefore, it can really be compressed into a much smaller size. Okay, but then you should sit down and calculate the density of what it will be, and the density is like of the order of 10 to the 14 or 10 to the 15 grams per cc. And what does that mean? 1 cc means 1 centimeter cube. 1 teaspoon of that material would be several thousands of tons in weight. Okay, and that you can say, well, that's unimaginable, but that is how it is. Okay, because that is the density in the nucleus of any atom. It does reach that density. Okay, now the other thing that happens is what is called conservation of angular momentum, which again many of you would have studied even at high school and college level, that if a body is spinning, it has a certain angular momentum, and if you conserve if you change the size of the object, if it conserves angular momentum and you shrink it and the same mass is there, then it has to start spinning faster. And the simplest example that is given when we all learn is that if you have somebody, this person skating on the ice rink, and if you spread out your hands, then your angular velocity will slow down. If you bring your hands in, then your angular velocity will go up, okay, because angular momentum is conserved. Okay, so when you do this, the star which is originally spinning, even the sun is spinning just like the earth is spinning at some slow sedate rate, that thing becomes a much faster spinning star, so much so that rate of spin can become once in a second. Now, once in a second is very fast, right? I mean, the earth goes around once in 24 hours, okay, and any of your typical motors that we make, few hundred RPM, okay, we are now getting into that kind of regime. And as I show later, we know now neutron stars which go spin at once in 1.7 milliseconds, which is like 700 RPM. Okay, so this object is going around, if I speak now a few sentences, it has gone around thousands of times in rotation. Okay, so now you say, wait a minute, what's going on? You have an object whose mass is as much as the sun. It is 20 kilometers in size. It is like almost comparable to the size of Mumbai city. It is spinning, and it is spinning at a rate of 700 times a second, or a few hundred times a second. So you say, wait, this can't be, okay, but it is there, and it is both predicted from the calculations, and now actually we have observations which support that such objects are there, and they do have these properties, okay. And to add to that, they have very strong magnetic fields also. So again, almost every object, Earth has a magnetic field that you would have heard about, like a dipolar magnetic field. Sun has a magnetic field, and again when any star has it, and when the star core collapses, again there is, like angular momentum conservation, there is conservation of magnetic flux also, and the magnetic field strength grows and becomes very strong. And so these things are inferred to have magnetic field strengths which are thousands of times stronger than any magnet that you can make in a lab, even the best magnets that are made which for various purposes. But the main thing is that it is very dense, and when it is very dense, it has very strong gravitational force. Okay, now the gravitational force depends on the mass of the object, okay, and how much of that force you feel depends on how close you can come to the mass, right? So the sun has a similar mass as a neutron star, but you can't get to 100 kilometers of the sun, because the sun size itself is so big, okay. So you will never feel that much force, okay. So if you take the same mass and put it in a very small confined space, and you come close to that mass, you will feel much stronger force than if that same mass was a bigger one and you were further away from that mass, right? And that is the way the gravitational force works. So these things have very strong gravitational forces, and also very strong magnetic forces, and so on. And much of this, as I was saying earlier, was worked out from the theoretical calculations and predictions that look, such things will form as a natural consequence of this evolution of these kind of stars. And people said, okay, fine, but how can you ever detect such an object and verify any of these properties? So then we'll talk about how it happened. Okay, so as I was saying in the earlier lecture also, many of the discoveries happen serendipitously, by accident. So in this case, there were these two astronomers, Tony Hewish and his student Jocelyn Bell, who were doing a certain kind of radio astronomy experiment with a radio telescope array in the UK, where they were trying to study the twinkling of radio twinkling of stars, just like stars twinkle, and we know that, and then that is because of propagation of the light of the star through the Earth's atmosphere, causing turbulence in the atmosphere, causing fluctuation of the light. In the same way, radio signals from stars also show the twinkling phenomena. And twinkling means some quick variation, right? So if you look at the star, and twinkling means its light is fluctuating at a rapid rate. And they were studying this radio twinkling of stars, and they were therefore recording data from some objects in the sky at fast enough rate that they could see the fluctuation of the radio signal with time. And when they were doing that, they saw this kind of a signal where some source was there whose intensity was going up, down, and like periodic. It's a bit like a ECG. So if you see this, you will say the nearest thing I know is a ECG. An ECG is exactly like that. Tuck, 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 tuck. It goes as pulses, and they detected this signal. And when they saw this, they said, "Look, no natural source in the universe that we know works like this." So initially, what happened? Two things, like when Karl Jansky was trying to find out, they thought this must be some interfering signal from some man-made source. Then they could rule that out, like Karl Jansky did. No, it's coming from fixed direction in the sky, not from the Earth. Okay, so then it was, well, this must be some intelligent being signaling to us. Okay, that's first. That was one of the first things that people said, and they were given some fancy title like Little Green Men. Okay, that somebody is signaling from somewhere, and you are seeing these signals coming from them, because this looks a very artificial kind of signal. Okay, but very soon they found that, look, it doesn't have the properties of something signaling to you. One, it is on all the time. Whenever you look in that direction, you see this signal. Okay, number one. Number two, they found that with time, slowly this interval is changing, very, very slowly. Okay, but it took many weeks of observing to find that this period is slowly increasing in a systematic manner. So they said, look, then they found one more in that direction, one more in that direction, one more in that direction, all with slightly different values of the period and slight difference in properties. So they said, no, there can't be so many little green men signaling to us from different parts of the universe. This must be some unique kind of object that we have found which has this property. Okay, and very soon then, based on various properties, one that there is a certain yes.
If we know some properties of a neutron star, then we can get to know the amount of time it takes between one detection and another detection, right?
You mean like time between these pulses?
Yeah.
Yes.
So what are the properties that we need to know?
Oh, in order to just detect the interval between the pulses, you don't need to know any other
I'm asking that, is there any other way? There must be some other way than just measuring the amount of time it takes between two pulses. So what is the other way to figure out the difference of time between two pulses?
Actually, there's no other way. I mean, that is the only way. What is done is basically you are observing the signal and you are recording this data as a function of time, and you are having an accurate clock with which you are recording this data in the observatory, and then you count the time interval. Okay. Now there are more sophisticated ways of counting it, but finally basically you are counting the interval and then estimating the period. That is the way that is done. Okay, so what happened finally, after various studies and inferences, the conclusion was made that this object, class of object, has to correspond to the neutron stars that have been hypothesized by the theoreticians based on these evolutionary scenarios of the stars. Now you may ask, how did somebody come to that conclusion? It's a long process because it goes by elimination. You say, what else could cause this signal? Okay, so they said maybe it's a white dwarf, rotating white dwarf, and then you can show that certain properties of these signals were such that white dwarf model will not fit. Then they said it could be two objects going around each other, and that this periodicity corresponds to the rate at which they are revolving around each other. That was again shown that certain kinds of properties are infeasible, not compatible with that. Various things. In fact, there were even models that even a single star, if it was for some reason oscillating due to some instability, and whether this period can correspond to the oscillation of the star, and that at one part of the oscillation this pulse is emitted, and that again was ruled out. So various theories were tried, and finally the only one that has survived all the tests of time, which is basically every such object found that theory should be compatible with it and all the properties, was that it must be a rotating neutron star which is producing this. And the model that has come is what is called a lighthouse model. So the simplest thing to think about, I think all of you have seen a lighthouse either in real life or in a movie or in any this thing. And in a lighthouse, what happens, there is an object in this case which produces a beam of light. Okay, you can think of a torch if you want, and it is going around, rotating. Okay, and so this rotation axis is like this, the axis of the beam is like this, 90 degrees, and it is just sweeping. So if you are in the line of sight, you will see one flash every time. Okay, that's what the ship sees, which is in the sea, and the lighthouse goes around. Okay, if you are not in that line of sight, for example, if you are vertically above the lighthouse, you are unlikely to see that flash because it is just going horizontally. Okay, so that was the model. In the more general sense, that angle between the rotation and the angle of the beam need not be 90 degrees. It could be 60, it could be 30. Okay, but the model still holds. So then it is a cone that is sweeping out instead of doing like this. And as long as you are in the line of sight of that cone, you will see a flash. Okay, so that is what this generalized picture is. This is the axis. This is a neutron star. It is rotating around this axis, and it has some beam of radiation, radio waves coming from another axis, which is the magnetic axis, and they are not aligned with each other. They could be 90 degrees, they could be any other angle, and as long as your line of sight as it goes around intersects, and that is what that model outside is, if you have seen that, and our attempt to illustrate that. And as that model, then where the beam cuts through the telescope will pick up that signal and be able to detect it. And so this is the simple animation of that, and so whenever that beam crosses a line of sight, you will see a pulse, and that is what these repeating pulses are. Okay, now of course the interesting thing is, how come this object with these properties, 10 kilometer size ball of neutrons and having this strong magnetic and gravitational fields, how does it have this, what produces the beam of radio waves, how intense are these radio waves, that how far do you go away from a lighthouse before the lighthouse signal becomes so faint that you won't see it. Okay, it's not too far away. Okay, after that time but these are lighthouses which are thousands of light years away. You can see them all over our galaxy. Okay, today we know around 2,700 such sources that we have detected, and it is estimated there are around 50,000 such neutron stars in our galaxy. Okay, so it's interesting that and that is where so the analogy becomes, and this again you will understand. So supposing so most lighthouses have normal lamps. If you put a laser beam in a lighthouse, okay, and you see all these laser beams in the shows, right? The laser beam penetrates to much longer distance. That's because it has a certain property called coherence in terms of the way the light is generated and emitted, and that allows it to be seen to much longer distances, and that is what is thought to be happening here also. There's some form of coherent emission. Okay, but you had a question? Yeah.
Sir, in this image, every alternate seems to have similar kind of intensity as compared to the
Yes.
Adjacent one.
Correct.
So does that mean that in that pulsar, one of the beams is exactly pointing towards us and
Yes.
the other one is
Correct.
not?
So that is because that angle is not 90 degrees. So in the lighthouse, okay, lighthouse has only one beam, but you could imagine a fellow having the one going the other direction. Then you would see two flashes from the lighthouse, one from this forward beam and the other from the backward one when it came in the front. Okay, but if you change that angle away from 90 degrees, then the forward cone will sweep one path, the reverse cone is sweeping a different path. You can't be in the line of sight of both of them, okay, given in one position. So that's why here you will see this angle is deliberately not 90 degrees, and you will see the beam only when one of those crosses the line of sight, and that's when it blows up, right? The other one is never doing that because it is always pointing in a different, it's sweeping out a different path.
And sir, the signal is kind of fading. I mean, it seems to go in a bell curve.
Yes.
So is that because of some kind of precision that whole star is going through?
No, that is not precision. It is just that beam has a certain angular spread. When you see the center, you will see the brightest. When you see the edge, it will be the faintest. So that's all that is happening as you cut across it. Because finally it has to go to zero, right? And it has to fall off. And if you want that to be square, then it has to be just equally bright beam which you are seeing all the time, which will not happen in most natural cases. Okay, so this is like a real life example of some data which is showing pulses, and as I was saying, these periods observationally people have now found that the shortest ones go down to about 1.7 milliseconds or so, and the longest one today now people have found 8 seconds, but now people have found something even longer. But typical number is like hundreds of milliseconds to a second as the rotation speed, and the typical range of frequencies over which they emit is in this 100 to 1000 megahertz, maybe up to 2000 megahertz kind of frequency range that GMRT works with. And even then they are fairly weak sources, as this is what we were discussing in the first lecture, that in astronomy, radio astronomy, all the sources are very weak compared to what you think is a strong source of emission, but they are strong enough that you can see these pulses in many cases. And this basic model is what I was already talking about, with the neutron star itself of about 1 solar mass kind of an object, and with very strong magnetic and this thing fields. Okay, now what I was saying earlier is that these were discovered in the radio, and then people ask this question: can I see these pulses in other bands, like in optical or in X-rays or in gamma rays? And as I was saying in the earlier lecture, that most objects don't, and so there are very few of these pulsars which are seen in any other band, but there are one or two which are not more now more than one or two which are seen in other bands, like in optical. So literally you can see it going on and off in optical images of the Crab pulsar, and this is actually the supernova remnant from where the explosion took place, and this is the core of that neutron star which is now being seen as a pulsar. Okay, then like I said, we'll just briefly talk. We talked in the morning, so I won't spend too much time describing radio telescopes, but you need a very powerful radio telescope in order to pick up these faint signals, number one. Number two, you have to be able to record. So you see, if you want to see the details of a signal which is repeating every 1 second, then your data must have resolution which is much faster than that, right? If you take data once in 10 seconds, then you will not be able to see the details of a signal which is fluctuating and varying in once a second. So you have to record data at fairly high speeds in order to be able to decode the signal and make sense of it. And this I won't spend, because I talked about this in the morning lecture as to what is the difficulty and how you make big telescopes. And this also I talked about it, that how do you combine signals from an array of antennas in order to make a very large telescope. And this is what we talked about when describing GMRT. So again, this I won't. So now we'll get back to neutron stars. And so in this, when we were to summarize that degeneracy of neutrons holding the core of the star together, 10 kilometer size, 1.4 times mass of the sun, so very high densities, very high rotation rates. Not only that, it is rotating, but it is rotating very stably. So Earth goes around once in 24 hours, but you would have heard that rotation rate of the Earth has small jitters, okay, and then there is a lot of precision measurements done to keep track. Okay, they are small, but they are measurable. In these fellows, the rotation rate is very stable, and you can understand that. So if if you say some quantity is very stable, that means I must be able to measure it with a high degree of precision. Okay, so if you say that my weight is constant, I'm very proud, I maintain it at 70 kgs or something, then you say I can measure your weight down to what, 100 grams or 10 grams or what. Okay, how constant are you maintaining it? Okay, so here, for example, you can measure the periods down to 10 to 12 places in decimal. Okay, so you say the period is 1.247865 seconds, and you can but you remember I said earlier that it is slowly changing, because you know why? Because you can ask, where did the neutron star get all this energy to spin up? Okay, so it spun up from the original reactions, that whole thing that happened, but it is losing energy all the time, and it is not getting replenished from anywhere. So therefore, some of the loss of the energy shows up as the loss in kinetic energy. So this happens in any object, right? If you start a top to be spinning, after some time the top stops spinning, right? It is why? Because due to friction and other things, it is losing energy, and when it is losing energy, that loss of energy shows up in the object slowing down, right? Which is true of anything. Even the moving objects, if you leave them, they slow down and stop. Why? Because they are losing energy, mostly due to friction forces, right? And so here also it is losing energy and it is slowing down, and you can measure this slowdown, but the slowdown is very, very slow. So it is like if I am going at 60 kilometers an hour and I am slowing down, okay, maybe I am slowing down at 10 kilometers an hour, so after some time I will come to a stop. Here the slowdown rate is something like 1 part in 10 to the 15. Okay, so and you say, well, how can that be? Can you measure it? And you can measure it because the rotation rate can be measured very accurately. So this is the thing that when you were asking, that you measure the time between the pulses, and you keep measuring this time accurately over days, months, years for the same neutron star, you will find the time between the pulses is slowly increasing, slowly, very, very slowly. So something which is spinning at 1 second today, 1 year later may be spinning at 1.000001 seconds. Okay, and you say, well, can you really measure it? And actually you can. Why? Because that 1 second is very accurate, and when it becomes 1.00001 seconds, it is still very accurate. Okay, so this stability is amazing. In fact, one of the things that is interesting, some of these are so stable that you can use it like a clock. So when you have a clock, what is the most important property of a clock? That all clocks are derived from some oscillation, right? Something which is, and it is very accurate oscillation that you are timing and producing a clock and saying this measures time accurately. Some of them rotate so stably that you can actually use them as possible time standards.
So it's losing energy just via its radio waves, or is there any source
Yeah, that's a good question. So, actually the main loss of energy is not because of radio waves. It is because of something called electromagnetic breaking. Since you asked it, I'll explain. So, as you saw in this picture, the magnetic field is a dipole, and it is not aligned with the rotation axis in general. So, this means that if you were sitting at any point here and this magnet is rotating, you will get a rate of change of magnetic field, okay, what is called dB by dt. And wherever you have a rate of change of magnetic field, you will get a rate of change of electric field from the basic theory of electromagnetism. That means that there is energy propagating. dE by dt and dB by dt means there is a wave traveling and taking energy, and actually you can show physically that any magnet, when rotated on an axis which is not its magnetic axis, will have this property that electromagnetic wave will be generated at the frequency of rotation, which will carry away energy by the Poynting flux.
That will be also electromagnetic wave, right?
Yes, but it will be at a frequency which is this 1 hertz if it is rotating at 1 second. That you won't see because you can't detect a 1 hertz wave by any of the typical techniques we talk about, and nor for that matter do we think it may even reach us that far. But the radiation that is produced, which is from a completely different phenomena, which also we don't fully understand, but it has to be some plasma process happening in the atmosphere of the neutron star, that produces radiation in this hundreds of megahertz frequency. But it is a small fraction of the total energy loss of the neutron star. The dominant energy loss it comes from a different mechanism, but the point is it is losing energy. Yes?
What causes the misalignment of this?
Okay, good. So we don't think we have a very clear handle on what causes it. So even in the Earth's magnetic field is not perfectly aligned to the Earth's rotation axis. Okay, and now you can ask. So people don't understand very well how these magnetic fields get oriented and how they change with time if they are. Okay, in fact, there is even some theories which say that with time in a neutron star, they starts to align and it will end after many millions of years. It will align like this. That's a theory. It's not proven to be verified, but the physics of how and what is not very well understood. It is thought that when there's very energetic events happen, like the supernova explosion, and at that time, even if the original star had these two aligned, it can disrupt that alignment. Okay, it's possible, but it's not a well understood thing. Yes.
What is the maximum possible accuracy? What is the minimum possible accuracy? What is the maximum accuracy observed, and what is the minimum accuracy observed?
Accuracy of what? Of these measurements that I was talking about?
Accuracy of the amount of time it takes. That it will
I mean, there's a period, na?
yeah.
Yeah. So the accuracies that we typically can achieve in these measurements are so they depend on how long you observe. Okay, and in many of these cases we can reach accuracies of 1 part in 10 to the 15 kind of a number, which means 14 decimal places after in the quantity that you're trying to measure. Okay, that kind of numbers, maybe not 15 but 12 decimal places kind of accuracy has been achieved in measuring these periods.
What is the maximum possible and minimum possible?
Maximum possible is hard to say. Like I said, it depends on how long you observe it, and it also depends that during that period when observing, nothing should disturb that fellow. That we don't know. Okay, we think that they are very rock steady and not disturbed very easily. So it's hard to put a number on the maximum possible accuracy.
Let's say there's nothing disturbing it, and 1 day. They're observing for 1 day.
Then you can work out what that accuracy will be in terms of, it is just a ratio of effectively the number of rotations that have gone by during that 1 day, kind of a thing. That will tell you the fractional accuracy with which you can get some of these things. Because you know what happens, what you are measuring is when do I see the peak of the pulse again, okay? And if you say, well, you know that I saw the peak of the pulse again here, and this is after it has gone through the number of rotations in 1 day, then that accuracy must be so much for the peak to come back over there.
Yes, but what is the maximum possible?
As I said, so if you make that 1 day,
Maximum for that neutron star particular, but for maximum possible for any.
that's why I said, so if you make that 1 day into 1 year, into 10 years, to 1000 years, then the accuracy will keep improving as long as nothing disturbs it. So it depends on how long you are observing it, finally.
I'm saying that you take 1 day
Hmm.
and it depends on maximum accuracy. It is possible for any neutron star.
For one day you can work out that number. What is that is basically the number of rotations of the neutron star that have gone into that.
Okay, but what is the maximum possible number of rotations?
Oh, that in this case will be the time of 24 hours divided by, say, 1.7 milliseconds. So you can work that out and see how much that will be. It's just that number which you can punch in your calculator, or maybe you can do it mentally also. It will tell you. Sorry? Okay, if you want to follow that one, we can follow it later on, that particular train of questions. Okay.
What exactly causes, why does this magnetic field become so strong while converting into normal star to?
Yeah, so see, like there these various concepts like conservation of angular momentum. Okay, there's a concept called conservation of magnetic flux. Okay, that applies under certain conditions. Okay, so and people believe that in these situations conservation of magnetic flux applies, which means that if you take a certain volume where there was a certain amount of magnetic field pervading in that, and you compress that volume, then the what is called the magnetic field density will keep going up, and which is what it means is that the field strength will keep going up. That requires the material to have certain properties, bit like conductance has to otherwise conservation of magnetic flux will not happen. So if
in normal star, whatever ionized gas they have, that motion of those ions actually causes the magnetic field.
okay, so now we are getting into territory where we see, for example, if somebody asks you what is the cause of the Earth's magnetic field. Okay, now there are ideas. Okay, molten core with this property. Okay, even here people
See, I want to ask, moving charges can cause the magnetic field. So here they don't have charge, no, because most of the matter is neutron.
Yeah, so that's where you have to now go into the physics of what happens in super dense matter, and there is a certain kind of physics which allows magnetic fields to be supported in super dense superfluid material, which like I said, this one lecture is not enough to go into that, but yes, so you're right that it's not that we have all the answers. So now you can say what does that mean? So there is a way of inferring something, and then there is a way of saying, well, can you show me a theory or a model which will support that inference? Okay, now the inference is quite strong. It comes from as simple as when I can see that it is losing energy, it is slowing down, I can measure that, I have an estimate of its mass, I know its moment of inertia, I can calculate the rate of loss of energy. If you say that rate of loss of energy is coming from that magnetic breaking, the dB by dt, dE by dt, then you can calculate what B has to be. That's a well-defined physics which does that. So now you've got a value of the strength of the magnetic field. It comes out to be 10 to the 12 Gauss. Now you ask, okay, how did this object come to have this? Then people theorize, okay, if flux was conserved, this would happen, that would happen, but What is the mechanism? We still don't have a complete answer. So it is part an inference from observed properties and part some theoretical model which tends to show how such a thing is possible. It's not necessary that the theoretical model is complete to the last detail. In fact, a lot of magnetic fields in the universe are things that we don't fully understand. How, why, evolving, everything has a magnetic field in the wherever we look, whether it's planets, stars, even the medium between the stars in the galaxy, the medium between galaxies, they are found everywhere. Now you ask how many charges flowing in what manner which produce. So we don't have this full complete picture of everything, but there is inference that there is properties which magnetic fields can only produce. So it must be there at this many Gauss kind of a number. So that's why this says inferred magnetic field. It is inferred from certain this thing. Okay, so all right. My goodness, it's 1:45. Okay, fine. I won't go into again details. So there are theoretical models of what, if you cut through the neutron star, what will you see? Okay, kind of a thing. And it's not that we understand everything, but this is what I was saying. That down here is superfluid, superconducting material with a crystallized neutron core. See, these are all postulates. Okay, there are models. It's not that you know this for sure. Okay, so this is what I was telling you about, how that loss of energy can be lead to estimate of the magnetic field just by measuring how it is slowing down and so on. Okay, and this magnetic field is, you know, much stronger than anything that you can create in the lab or anywhere. Okay, and the interesting thing is that in the neutron star there is this competition between gravitational force and electromagnetic force, because you have such strong gravity, you have such strong magnetic field. You can ask that what happens if I put a charged particle just above the surface of the neutron star, like a test particle. If you were to produce, what will happen to it? Will gravity dominate or will electromagnetic forces dominate? Okay, and this is an interesting this thing, that although you would have said, look, this is the strongest gravitational force, this electromagnetic force dominates over gravity by 13 orders of magnitude. Okay, so that tells you that once you talk about what will happen to charged particles, it is the electromagnetics which dominates, and that's what is thought to produce this radiation that we see as these radio waves. But again, we won't go into the details of that, because we ourselves don't have a working theory of how you can explain all the properties of the radio emission that we see. But this is the closest that we have as a model of what happens, which is that you think of it as a dipolar magnetic field, like a bar magnet with an axis which is not aligned to the rotation axis. And then when you spin this, so there's very interesting things that happen. So when you spin a 10 kilometer size ball at a millisecond rate, you can ask, so you know that the V equal to r omega. So V is just the velocity at which it is rotating at any distance r. Okay, so you know omega, the rate at which it is going around. So you can ask that at what distance from the neutron star this speed of rotation would become equal to the speed of light. So you say, what, is that possible? Yeah, it's possible with any object, right? The earth is going around at a certain speed. We are sitting on the surface of the earth. We are going around at some speed, which is of the order of meters per second. It's not a negligibly small speed, okay? It's faster than most speeds that we do with any man-made activity like vehicles and these things and so on. But if you were attached to the earth and kept going further and further away, that speed keeps going up, right? Just V is equal to r omega. And at some very distant place, if you still had connection to the earth, you would reach the speed of light. Okay, but it's a very, very far distance. For this kind of object, because omega is much faster, that happens within a few thousand kilometers from the star. Okay, so which means that matter which is in the magnetosphere, it cannot co-rotate with it. because as per the postulated, nothing can go faster than the speed of light. So at this point, what happens is magnetic field structure has to break, and this I won't go into the details of that, but just to say that there's a part of this magnetic field which behaves differently, which belongs in this open field line region, and the part of the magnetic field which is here in the closed field line region. And all this activity that we think produces radio waves happens in a narrow cone in this open field line region, and radio waves are generated again from inferences from observed data. We infer that the radio waves generated of the order of few hundred kilometers above the surface of this 10-kilometer star object. So it's something happening in its atmosphere, which is what we call the magnetosphere. And again, I can't go into the details of that, but but what we can talk about is what we see. So we see those pulses that I showed you. The pulses come regularly over a range of frequencies, but due to the interstellar plasma in our galaxy, the pulses are delayed and they travel at different speeds at different frequencies because of the plasma dispersion. But we know how to sort of correct for it and account for it. But if you look at a typical pulsar signal, from pulse to pulse there are strong variations, but you will get an average shape of the radio pulse, which characterizes how the pulsar works. And I won't go into details of this because already we are running out of time, but a lot of detailed understanding has been developed about what the nature of this emission may look like, but we still don't have a very good theory of exactly what can produce this, and that is part of a lot of the research that we still do. In addition to that, you can, as I was saying, you can use these as very accurate clocks, and you can measure the interval, you can measure the change of the interval, and you can measure anything that causes this interval to change, like a Doppler motion. So if you know this, that if you are measuring any periodic signal and it is on a frame of reference which is moving with respect to the observer, then the period of that signal will change. This is the Doppler effect, right? And this is famously explained that if you have a whistle on a train and the train is moving, then the pitch of the whistle will change, which means that the frequency of that signal will change. And in this case, the frequency is the separation between the pulses. And since these things are such accurate clocks, very small changes in these can be measured. So for example, as the Earth is going around the Sun, okay, supposing Earth is going around like this and there is a pulsar in that direction, then when the Earth is going like this, it is going towards the pulsar. When the Earth is over here, it is going perpendicular to the pulsar. When the Earth is over here, it is going away from the pulsar. So between these two observations 6 months apart, you will see that the speed of the Earth with respect to pulsar is opposite, and it will produce a Doppler effect where the period of the pulsar will increase, go to maxima and then decrease, and then come to a minima and then increase. And so you can ask, how much is this effect? Again, this effect is like at the fifth decimal place. But since you can measure this thing at 12 decimal places, you can very easily see this. Okay, so this is an example where the Earth is moving, but if the pulsar was moving in an orbit, okay, due to something, you can see that also. And that becomes interesting because Earth's motion you know. But supposing you had a neutron star which was in a binary orbit around another object, it can be a normal star, it can be a neutron star or whatever, then this thing would be happening. So I think I have a picture somewhere. Let me, these are all the details about the observations and the theoretical models. So time, okay, so yeah, so imagine a situation like this where there are two objects going around the center of gravity. One can be a neutron star, other could be a normal star, it could be a white dwarf, it could be anything. So as this fellow moves, its velocity with respect to us can be changing. Just like I showed, then the Earth's velocity is changing, which means that its period will change in a cyclical manner. Okay, and this change can again be in 5th decimal place, 4th decimal place, 6th decimal place. Then now that depends on the speed of that fellow. But you can detect this. Once you can detect it, then you can infer what kind of orbit it is moving in. Once you can infer what kind of orbit it is moving in, then there are other measurements you can do, and you can say, hey, this must be a binary system with a companion of this kind of mass, and they are separated from each other by this much distance, and so on. Okay, so now you can see that, wait a minute, so from this you have actually been able to infer what kind of environment this neutron star is in and what kind of thing it is doing. You say, that's nice, okay, that's good. Now this thing becomes interesting. Supposing it is in an orbit with very close by, okay, and then the two objects, say the neutron star there's another neutron star, and they're coming, let's say, 2000 kilometers from each other. Then they are feeling the force of gravity, which you cannot easily generate in any other kind of experiment. Okay, and so this is, so what happened from Newton to Einstein. What happened? So Newton had a theory of gravity. Okay, what Einstein said is that, look, this is accurate enough under certain conditions, but under certain conditions, when you go to higher gravitational field strength scenarios, this theory is needs to be modified. So that's what Einstein's theory did. Okay, and now you can ask that under certain conditions, is Einstein's theory also an approximation, and is there something more accurate and more correct which applies, which can only be found or tested when you are in situations where you have a very intense gravitational field, because in all the other circumstances you have a theory which works. Okay, and that's that's how science proceeds, that you have a theory which works under a certain regime, and then you find a regime where this theory doesn't give the right answer, and you say, well, there has to be a more sophisticated theory that has to answer this, and so on. And theory survives as long as there is no observation which refutes that theory, right? And the moment that happens, you have to say, well, there has to be a better theory, a more refined one, which does this. So this is one of the big questions that has been asked, and so far, whatever measurements that have been done using neutron stars have shown that whatever Einstein predicted is correct. But people still ask, can I get to a regime where I'm pushing the theory to the limit and asking, is it still correct? And this is the only laboratory in the universe where you can do this. Okay, so I won't go into more details than that, but this was the first time that people showed this, that the change in so today gravitational waves is a big thing, and one of the big things about this exhibition is LIGO and the ability, but again, gravitation was predicted theoretically from Einstein's theory that such a thing should happen, and people said, well, what evidence do I have? So first time they showed that two neutron stars coming so close to each other in their orbit that they are losing energy due to gravitational wave radiation. The extreme form of that is what LIGO picks up when these two come so close that they coalesce and combine into one object. That last phase, which is the most intense burst of gravitational waves, is what LIGO picks up. But well before that, thousands to hundreds of thousands of years before, when these objects were coming closer and closer and closer, they're already emitting gravitational waves at a much weaker level. Those they could show that the way the orbit is shrinking by just measuring this timing, that this is consistent with the theory of gravity of Einstein, and this is 20 years of observing. And what are they doing for 20 years? The same thing, measuring the tick, when the tick came, when it came today, when it came tomorrow, when it came next year, when it came 10 years later, and asking how is that interval changing. So that is the accuracy of that measurement and the ability to fit a model to that measurement, which shows that this slow change in the properties can only be explained by a model which is consistent with Einstein's theory. And that was thing that got a Nobel Prize for doing this experiment and showing that this is the indirect proof that gravitational waves exist and are being generated. All right, so I think this is a good point to stop here, because we are almost at 2 o'clock, right? Normally this lecture should be up to like 1 o'clock or something, right? But sure, anybody has any questions, we can talk for some more time. I'm sure he has more questions. I'll talk to you separately. Let me get other questions first. Huh? We'll have lunch together. We can talk for a long time. Yes.
Is there any kind of statistical survey done that we have, at least for our galaxy, that we have these type of stars more, like having mass of range this and that?
You mean overall?
Yes. At least for our galaxy.
Yeah, overall there is now a reasonably large sort of collection of information about the range of stellar masses in our galaxy, how many of what kind and so on, though there are still some uncertainties about the exact thing, but there is now quite a good understanding.
As you said, the rate of burning of heavier stars is low. Means the probability of finding black holes and neutron stars are much more as compared to white dwarfs. Is this any kind of information available?
And when it comes to probability of finding different objects, that's slightly different. So in any such thing, what happens is, so suppose you just took one big cloud, huge cloud, and you asked that if this was going to break up into smaller clouds from which stars form, how do you expect a cloud to break up? Will it break up into lots of large clouds from which big stars will form, or will it break up into lots of small clouds from which sun-like stars will form, or will there be a hierarchical such breakup? Normally the breakup will be hierarchical. In any such breakup, the hierarchical structures are such that there will be fewer of the bigger objects and lots of the smaller objects. You think about breaking up anything and doing this, and it is often a natural this thing. It's a different matter that the few bigger objects carry lots of mass or lots of any other property, but if you just want to count the numbers, okay, then it's always that there will be lots of normal and faint and small objects and few bright big outstanding fellows. Okay, you know, it's like you can see this in many other kinds of distributions. That generally happens in this kind of thing also. In some sense, it tells you that as per this initial function, the number density of these smaller normal things will be higher, and of the bigger fellows will be less. What it does not tell you is that whether these things evolve further. For example, will many of the smaller ones get a chance to come together and become bigger after they have formed stars, which does happen, and that is true even with galaxies, not just stars, you know. So that is therefore a bit harder to answer as to whether the probability of white dwarfs, finding white dwarfs is higher than probability of finding neutron stars or black holes. A little bit of also depends on your ability to find something. So there's a separate question: is the number density of these larger versus the probability of finding this is higher or not? But what happens generally nowadays, the techniques for finding are very varied. I mean, because the technique to find a black hole is very different from the technique to find a neutron star to the technique for detecting a white dwarf. They're completely different. They depend on different kinds of signals, therefore different kinds of telescopes, therefore different kinds of technologies, different kinds of uncertainties and so on. Yes?
Sir, there was one mention about Mercury perihelion precision. Can you move on to that slide?
Yeah, where was that?
I think the previous slide. Yes.
Yeah.
Sir, so over here, if I'm understanding it correctly, the gravitational waves produced by pulsars I mean, pulsar should be spinning at a faster rate,
Faster than?
faster than Mercury.
Yes.
Here you also mentioned that Einstein's equation is the solution to Einstein's some approximate solutions to the Einstein's equations are used so as to get better understanding in both of these cases. But in Mercury's case, I think we have a weak field gravity and near zone physics. But in case of pulsars, it is very strong field gravity. So what kind of approximation method do we use over there?
So I agreed with everything that you said except your middle statement about approximation. So there is no approximation being done. What one is asking is, in the case of Mercury, as you said correctly, that it is a weaker field test because Mercury is much further away from the Sun with the same amount of mass that the Sun has. The neutron stars and the companion come much closer than Mercury and Sun do. Therefore, the gravitational field that they feel of each other is much stronger than what Mercury feels of the Sun. So you are testing different regimes of gravitational field, and that's the reason. So people said that, look, with Mercury at that level of gravitational field, we have verified Einstein's theory and it's correct. Okay, there is no approximation there. That's why I was wondering about. So people said that this matches. Now, if I could take Mercury to be 10,000 kilometers from the Sun, can I still verify that the results or behavior matches with the theory? Okay, if I can take it 1,000 kilometers from each other, can I verify? That is what is happening in this regime. That is what you call strong gravity regime.
Sir, I might want to rephrase over here because what I meant by approximation was approximate solutions to the equation. Post-Newtonian approximation that we use for Mercury period precision.
I mean, it's correct that there are different post-Newtonian terms and you can do that, but to whatever level the phenomena has been observed, it matches with whatever terms you think are relevant in the post-Newtonian regime. I'm just trying to dissect your question about whether there are higher level post-Newtonian terms which have been neglected. That is, I mean,
case of Mercury, I
yeah.
think until 1.5 and up till 2 also it is very accurate, but beyond that it is very unnecessary.
But it's not the case that it has been shown to be wrong beyond that. Maybe the measurement is not precise enough to test it beyond that.
That might be
Yeah.
because these are numerical methods.
That may be true. Maybe I'll sort of think a little bit about what you're saying and see.
So I wanted to ask, what kind of solution methods do we use for strong field gravity? Strong field regime. Because even here we have near zone regime and strong field.
Okay, I'm not that much of an expert to say what solution method we use, but what I do know is that whatever those theoretical modeling produces gives predictions saying that you should be able to measure this feature of the binary system because of the Einstein's theory, and this feature will then produce this kind of a measurable quantity, and then we as experimentalists go out and try to measure that quantity and ask that is that measurement consistent with this prediction. Now your question is, so I'm not sure about what goes strictly into that prediction, if that is what you're asking. I'm not very sure about that part of it. Yeah. Okay. Anybody else? Yes.
So what happens when the pulsar is going to exhaust all of its energy?
Yeah, good question. So we are not sure. So yeah, okay. since you asked, so this is a diagram which shows the period, that basic quantity, and the rate of change of the period, that slowing down of the pulsar. Okay, so if you take any pulsar, you can measure these two quantities experimentally from this timing, and it will occupy a point on this diagram. With time, as we saw that the period will lengthen, it is increasing, and the period derivative will also change if it has a constant magnetic field. So these lines which are drawn like this would be the path of evolution of any pulsar. So today, let's say I take this pulsar sitting over here with this values. With time, it will move like this in this diagram. Okay, now you say that doesn't answer my question. What happens to it? Okay, now the one thing we know is that the physics of this emission, that which we still don't fully understand, but we know that it requires a certain combination of magnetic field and period, that we think in order for the physical process which generates the can generate this plasma, which can generate this coherent emission, radio emission. That process probably will cease below a certain threshold of magnetic field and period combination, which is shown by this gray region of this diagram. So for example, if a pulsar is moving in this direction, when it crosses this point, one thing that may happen is that this this radio beam will probably switch off. Now, do you call that the death of the pulsar? The neutron star is still there. It is still slowly spinning down. It is still moving in this direction. Now, you can ask, what is the ultimate limit of that? Okay, it will become a slower and slower spinning neutron star, but it may probably last for billions of years. Yeah, I mean, at that point, the time scale of that fellow living is as long as the characteristic time scale of the universe that we know. Okay, so then at that point you say, well, it is literally going to live forever once it is formed. But it may end up at a state where it's no longer energetic enough to produce the electromagnetic radiation because of which we see it as a pulsar. So the torch in that lighthouse may go away, but the lighthouse may still be slowly still spinning. Okay, any other questions? Yes.
So, as you told that